So we can use the tissue modeling capabilities of ASAP to model different disorder and disease states, and also to model certain treatment types, such as photocoagulation. So what we can see here is we have a skin model with a stratum corneum, epidermis, and a dermal layer, and is also filled with blood vessels. And the rays propagate through and are depositing energy within the volume. You can hide those rays and take a look at the energy distribution. And this is at 350 nanometers wavelength. And we can see that we have a fairly large spot on the layer of the blood vessels where energy is being absorbed outside of the blood vessels. We can also hide the blood vessel wall and see that we have relatively high energy absorption in comparison to the energy absorbed outside of the blood vessels at this layer. Now, if we grab this layer and we drag it up into the epidermis, we can see an even higher energy absorption here. We can compare that to the same basic geometry, but with different optical properties. These optical properties are at 560 nanometer wavelength. We can hide all of our layers once again and only take a look at the rays that are scattering in the system. And as we can see, there's a large number of rays that have actually penetrated within the dermis and have scattered around, versus the previous model, which we could only see a very few number of rays within the dermal layer. If we take a look at the same sort of energy profile in this 560 nanometer trace within the blood vessels, we can see, hide these blood vessel walls, we can see energy absorbed within the blood vessel wall, and also a lower amount of energy absorbed in the epidermis overall. We have different ways of viewing this as far as display properties. We can go to an isometric view, and this is a very clear view of how our energy is absorbed in the system. You can see a small amount of absorption in the stratum corneum, and then a huge spike in absorption in the epidermis, and then a fall off. And within the dermal layer, we can see very small spikes where energy is actually reaching the blood vessels. Comparing that to 560 nanometers, we can see a relatively small amount of absorption in the epidermis, still some epidermal absorption, but then in comparison, a huge amount of absorption in the blood vessel. So as far as treatment efficacy, 560 nanometer wavelength light is much better at dealing with photocoagulation than 350 nanometer light, because you're going to have collateral damage as far as the skin is concerned here. So let's take a look at how we would accomplish tracing these particular examples within ASAP. The first example we'll look at is the 350 nanometer blood vessel model. We've got stratum corneum, the epidermis, and the dermal layer, as well as the blood vessels. This is a model that was created using the realistic skin model in ASAP, and therefore it's a wavelength dependent model. Each of the tissues that we see has specific absorption and scattering characteristics that are unique to that particular wavelength, in this case 350 nanometers. What we can see is we can see a lot of rays that aren't penetrating within the dermis. They're actually stopping in the epidermal layer, and a small amount of rays that are actually getting to the dermis are getting into the blood vessels and basically dying in the blood vessels, being completely absorbed. Now, this is a qualitative analysis as far as where our light is going. We can look at a more quantitative analysis, which is our voxel system and the isometric graphs and picture graphs that we have available. As we can see, and we've seen before, we get a very high absorption in the epidermis at 350 nanometers wavelength, and very, very faintly we can see the blood vessels within the dermal layer here. but the energy that's absorbed in those blood vessels at 350 nanometers is very small in comparison to the high absorption in the epidermis. Once again, we can see in the isometric view of this particular trace, high energy absorption in the epidermis, low energy absorption in the blood vessels. Now, comparing that with the same skin tissue phantom at 560 nanometers, we have the same setup: stratum corneum, epidermis, dermal layer, blood vessels, the same geometry, but the optical properties have changed due to the fact that we've changed the wavelength of the light that we're looking at. So light will propagate through this system very differently because we're looking at 560 nanometer wavelength light versus 350 nanometer wavelength light. And we can see a much larger number of rays propagating into the dermis, getting to the blood vessels, and also scattering around within the dermis and getting to blood vessels that are outside of the range of our source, which may be incredibly useful for treatment applications. Looking at a pictorial representation of that, we've got relatively low absorption in the epidermal layer, and we can see a profile here of the low absorption in the epidermis and then high absorption in the blood vessel wall. And if we return to our isometric view, that's also reflected here as low absorption in the epidermis, high absorption in the blood vessel. So to summarize, we can use skin models and other tissue phantoms within ASAP to examine treatment efficacies based on wavelength so that we can optimize optical systems in order to better serve the patient as far as creating an optical device.